So let's go over we're going to jump into chapter 2, starting with section 1, and try to get these through the first 2 sections. And this won't be on your test, right? But you are going to have to do the homework and be ready for a quiz next week that's over this material, all right? You've got a little bit of work between now and then. That's why I would recommend that you get your test knocked out quickly while the chapter 1 material is fresh on your mind, and then move on to chapter 2. Okay, so let's talk about conditional statements. Conditional statements that are in what we call if-then form. If they're in if-then form, they will contain if-then, whoops, that's not supposed to be a plus, that's supposed to be a dash. So if a conditional statement is in if-then form, it will have a hypothesis, and it will have a conclusion. And that'll be important if you ever take my chemistry class. So never mind, that's not here, so never mind. But you have to know this when you're doing things like writing lab reports and stuff like that. We'll ask you guys, in the other science classes, what's your hypothesis? And then you'll have to have a conclusion at the end of that. So these should be terms that you're already familiar with. But so they give us as an example, they say, if it is, and I love this because this book was not published here, if it is noon in Georgia, then Alabama's going to lose to UGA. That's not the one state says. But if it is noon in Georgia, then it is 9 a.m. I would say to Georgia Tech, but we almost never see Alabama. And realistically, is Georgia Tech ever going to beat Alabama? I don't know. It hasn't looked promising in many years. If it is noon in Georgia, then it is 9 a.m. in California. All right, so there's our if-then-else statement. Our hypothesis, if it's noon in Georgia, then the conclusion, it must be 9 a.m. in California. All right, so just making sure that you understand if-then statements, you know how to read those, you know how to identify each part. So they give us some other examples. 2 points are collinear if they lie on the same line, and they ask us to rewrite that in if-then form. So 2 points are collinear if they lie on the same line.
If 2 points are collinear, then they lie on the same line.
So if 2 points lie on the same line, then they're collinear.
You can do both.
And actually, we're going to go there as we go on through this chapter. But you're right. Technically, for this one, since we haven't learned about the converse of statements, you could sort of write it in any order. They already have the if part with the end of it there, if they lie on the same line. So it would sort of make sense to me with the way this is phrased that maybe we would put that first. But in the example that they do, the solution that they have for the example, they put the 2 points. They just keep it in the same order. So they say if 2 points lie on the same line, then they are collinear. How about all sharks have a boneless skeleton? What might be, if you can do it without looking at it, what might be a way? You didn't look at it?
Well, I looked at it, but I have a different one.
Okay, all right. If all sharks have a boneless skeleton, what's your if then?
Okay, what was it again? I had a different one than this one.
All sharks have a boneless skeleton.
If a fish has a boneless skeleton, then it is a shark.
Then it is a shark. Good. And the way they do it in the reverse order, if a fish is a shark, then it has a boneless skeleton. But I would accept either of those, right? Mm-hmm. So you're just transforming it into an if-then statement. If the last one says a number divisible by 9 is also divisible by 3.
If a number is divisible by 9, then it is divisible by 3.
If a number is divisible by 9, then it is divisible by 3, right? So if-then. Everybody good with that? Did anybody? I think everybody that responded is on the board. All right. So let's find out what well, it does make this note. Conditional statements can be true or false, right? So we have to analyze these statements to see are they true or false. And to show that a conditional statement is true, you must present an argument that the conclusion follows for all cases. So it's a lot harder to prove that it's true than it is to prove that it's false. Because if you're going to prove that it's false, how many instances do you have to give me? Just one, right? You just have to give me one counterexample, one example where that statement is false, and then the whole thing is false. But in order to prove that it's true, you have to convince me that it's true for all conditions, right? So they ask us to, if I have this if-then statement, if x squared equals 16, then x equals 4. And they say, write a counterexample to show that this following conditional statement is false. Somebody that hasn't answered yet, whose name is not on the board, can you give me a counterexample for that?
This is true because at 4 with an exponent of 2 is 16.
Okay, that is true, what you just said, but remember, when we say something's true, we have to prove that it's true for every case. Will x always have to be 4 just because x squared equals 16? Joshua?
Would the 4 be able to be a negative 4?
Yeah, could x negative 4 satisfy that, Joey? If x was negative 4, x squared would also be 16, right?
Yes.
Right? And so what Joshua gave us was the counterexample, right? One example, one statement that we can make that disproves this is that if x equals negative 4, that would be a counterexample. Yes?
I thought you just said if x equals negative 4, could it satisfy this? And
Okay. Yeah, so x equals negative 4 would be a counterexample that would disprove this conditional statement here, right? Because this statement sort of draws the conclusion that x will always be 4 if we say that x squared equals 16, but that's not true. X could also be negative 4. So this is our counterexample that disproves it. It makes that original statement false. Is that clear to everybody? Just have to give one example where you disprove it, and then you can say that this is then false. All right, so let's talk about the converse of a conditional statement. So the converse of a conditional statement is basically what we were doing just a minute ago, where we flip it around and sort of say the same statement in reverse. So they give an example in the book. If you see lightning, then you hear thunder. And so if I tell you that the converse is like the reverse of that, what would you guys say would be the converse of that statement? Cal?
If you hear thunder, then you see lightning.
Yeah, there you go. So we just replace the if portion with the then portion on the other one and vice versa. If you hear thunder, then you see lightning. So if two segments are congruent, then they have the same length. We would say that is a true statement. That's the definition of congruency, congruent segments. If two segments are congruent, then they have the same length. How would I state the converse of that? Somebody that hasn't answered yet. Someone want to take a stab at it? If two segments are congruent, then they have the same length. Give me the converse. Yes?
If two segments are congruent, if two segments have the same length, then they're congruent.
If two segments have the same length, then they are congruent. So we're just giving you the same statement, but in a reverse order, right? All right, everybody clear on that? Converse? A statement can also be altered by negation. So what is negation? You guys see now why I'm letting you have index cards, all these definitions? Let's talk about negation. I should be here. Mr. Walker, we love you so much, right? You're great. Thank you for index cards. I just can't imagine having to keep all this stuff straight if you don't have something to. It's pretty easy on the first test. You could probably get by, but it just gets complicated. quickly. So a statement can be altered by negation by writing the negative of the statement. So simple, right? The measure of angle A equals 30 degrees. What would be the negation of that statement?
Measure of angle A is 30.
Yeah, measure of angle A does not equal 30 degrees, right? We just negate it. Just put not in there, right? If angle A is acute, then the negation of that statement would be angle A is not acute, right? Why do we need to know this? Because that will help us write what we call the inverse and the contrapositive of a conditional statement. So we're going to list all these down. Here's our original statement. And then we'll do the converse of that statement. And then we'll do, they actually did inverse next. So we'll do the original statement and then the inverse of that. And then we'll do the converse. And then what we call the contrapositive. And so the way that we write these is, we know we've gone over how to do the original and the converse, and we've gone over negation. And so the inverse is just the negation of the original, and the contrapositive is the negation of the converse. And that's why we did them in this order here. So we'll do an example here. If the measure of angle A equals 30 degrees, then angle A is acute. Right? Everybody agree with that?
What is the contrapositive again?
Okay, we're going to do an example. So I'm going to
Okay,
show you
because
as
I
we go
remember,
through it.
like-
Yeah, I just wanted you to be aware of them, and now we're going to do it. It's the contrapositive is the negation of the converse,
Okay.
whereas the inverse is the negation of the original. Okay. In fact, I'll write that out next to this. Negation of original. And this is the negation of converse. Alright, so if we negate the original statement, then we would say if, this is supposed to be if and not in, sorry about that. If we make everything, we negate everything in this statement. If the measure of angle A is not 30 degrees, then angle A is not, see how we added the not in there? Acute. So we negate both the hypothesis and the conclusion of that conditional statement. Yes,
Isn't that technically a false statement?
it is.
Just making sure.
Yep. We're gonna talk about that at the very end, but you're right.
It could be.
It could be, but remember,
It could be true, but
when
we
we
only
make
have
a
to
statement
think
like
one
this,
thing.
we're going to say whether that statement's true or false. And in
Yeah.
order to prove that it's true, we have to prove it's true for every case.
Right.
But we only have to give one example that makes it false to prove that it's false, right? And we could easily give an example of this, right?
Mm-hmm.
If angle A was 45 degrees, it would still be acute, right? It wouldn't equal 30, but it would still be an acute angle. So now let's do the converse. What would the converse of the original one be?
If it wouldn't be. It would
Remember
be,
with the converse, all we do is we take the if in and we switch them around?
Yeah, if
Yes.
angle A is acute, then angle A equals 30 degrees.
That's right. If angle A is acute,
Measure of angle A.
then the measure of angle A
Oh.
is 30 degrees. Is that a true statement?
No.
No, that's not true either, right? We don't know that for sure. And so now we're going to negate the converse. And that's what a contrapositive is. And so we'll say if angle A is not acute, that's supposed to be a then right there. Then, yeah, that was supposed to be a then, not a the, sorry. Then, so if angle A is not acute, then the measure of angle A, this should have been equals, we'll make this not equals 30. Is that a true statement?
No.
Yeah.
Yeah.
Yes.
Right.
Wait.
If it's not acute, then we know
It
Oh, yeah.
cannot equal
that
30.
it can't equal 30, right? And so what we see, what you'll usually find with these statements is that these outer ones will be the same, and these inner ones will be the same. So the outer set will, like in this case, be true, the inner set will be false. If you write them in this order, original, inverse, converse, and contrapositive. All right, so we're going to have to kind of feel like we're dragging our feet a little bit. I'm going to jump forward just a tad because I think you guys are kind of getting that. Everybody follow this? This makes sense going through this example? There's another example in the book that you can walk through. They make a statement if there's snow on the ground and flowers are not in bloom, and they show you how to do the inverse, converse, and contrapositive of each of those. But we need to look at these postulates here and make sure we're familiar with these. And they're kind of long, and so since they're long, I'm not going to write those out because we'd spend the next 10 minutes of me writing them out and you copying them down. All right. But let's just go through these real quick and make sure that you understand each of these postulates. Remember, postulates are just statements that are assumed to be true, and they form the foundation on which other statements are built. And so we're eventually going to get the theorems in here. And so we'll sometimes use these postulates to state that we say this theorem is true because of these postulates here or this postulate here. So the first postulate, postulate 5, says through any 2 points there exists exactly one line. Through any 2 points, we could draw 2 points anywhere on the board, and would you agree that through any 2 points there exists exactly one line, right? There's only one line that will go through both of those points. So we agree that that's true. That's postulate number 5. Now listen to postulate number 6. A line contains at least 2 points. So I think we would also agree with that, right? No matter how tiny I drew the line, there's room for a couple of points on there. So a line contains at least 2 points. If 2 lines intersect, they intersect at exactly 1 point. That's postulate number 7, right? And I would recommend, I'll just go and tell you, I would recommend putting these postulates on your note card. You have a question that's relevant?
So, does a line have to be straight?
A line does have to be straight.
Got
Yeah,
it.
by definition, a line is straight. Yeah.
Okay.
So yeah, straight line is redundant language, right? Because lines are always straight. Even though I still accidentally say it sometimes. But these postulates are going to be the basis for. Did you guys feel that earthquake? Everything just kind of vibrated for a second. Did anybody feel that? And they'll feel it on the video, definitely. You bumped the tripod. There it is. Yeah. Oh, there it is again. I totally lost my train of thought. These postulates. So when we start doing proofs and we start saying that we believe this is true because of da 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 da, and we start listing those out, you're going to have to refer back to these postulates. And I mean, sometimes we'll be doing a proof in chapter 7 or something like that, and it'll be referring back to a postulate that we learned in chapter 1. So that's why you need to write these things down and keep your index card from your previous test, because you may be building a new index card that has some of the same information on it. Okay? Does that make sense? And those index cards will be a great way to study if you have a test that like covers an entire semester or something like that. All right. So postulate number 8 says through any 3 non-collinear points there exists exactly one plane. So if I draw 3 points that are not collinear, in other words, I don't draw them like this where they're all in a straight line, right? But I draw them to where they're like this, so they're not all on the same line. Then there is a plane defined by those 3 non-collinear points. There exists exactly one plane. And we remember, like with a plane, we kind of draw it like this, but we understand that the sides just go on infinitely in every direction. Postulate 9 says a plane contains at least 3 non-collinear points. So are you starting to see with what we just learned about inverses and all this stuff that we're sort of 5 and 6 are related together? How they kind of flip the definitions around, and 8 and 9 kind of flip the definitions around. Through any 3 non-collinear points there exists exactly one plane. And then we sort of say the reverse of that. A plane contains at least 3 non-collinear points. Postulate 10, if 2 lines lie in a plane, the line containing them lies, if 2 points lie in a plane, then the line containing them also lie in a plane. So if we've got 2 points here, and we've already said that through any 2 points there exists one line, then clearly if the 2 points are in that plane, then the line is also in that plane. And then postulate 11 says if 2 planes intersect, then their intersection is a line. And I am not going to try to draw that picture that's at the bottom of page 73 because I would probably totally mess it up. But you see, let's see if I can do it. Let's just see. Let's see. So drawing one plane is easy, right? But drawing the other, so kind of like this, and goes down like that, and like that. There we go. Okay. And then right here.
Yay!
Nice. That's not too bad, right?
Yeah.
We've got a line that goes through there. It's the coloring helps though in the book. And so there's wherever those planes intersect, there's exactly one line right there. Their intersection is a line. Okay, any questions just as far as understanding those postulates? Does that make sense to everybody? They're just true statements. We accept those as being true. But we will build theorems off of those in the future where we're using those statements, combining those statements together. All right, I'm going to jump on to chapter 2.2. And let's talk. What's that? Did you say okay? You give me permission, David? So your last name's Waterhouse, right?
Yes.
Every time I think of your last name, I think of Mr. Waternoose in Monsters, Inc. I don't know if you've ever seen it, but I think of that. I want to call you David Waternoose, you know?
That's hilarious.
So, yeah, right. I didn't vote for that. So, perpendicular lines. What makes 2 lines? What makes 2 lines perpendicular?
The fact that they intersect with right angles.
At right angles, that's right. So if we have this little, that's how we identify a right angle, right? It's the little square there in the corner. If we have this little square in the corner of 2 lines, then we know that they are crossing perpendicular to one another because they cross at 90, they form a right angle or a 90-degree angle, right? So perpendicular lines, that's just a definition that you should know. Perpendicular lines intersect to form right angles. And we could also have a line that intersects a plane. And so if we drew a line like this, the point at which it intersected the plane, this is kind of weird to draw, actually. I should have done this, sorry. Where it hits the plane right here. Well,
Looks like a weird picture.
yeah, comes through, it's hidden behind here, right? And then it comes out right there. So it kind of goes into the plane there, and at this point here, and we've got like a 90-degree angle right there as it intersects the plane. So a line perpendicular to a plane is a line that intersects the plane in a point and is perpendicular to every line in the plane that intersects it. So every line that's in this plane here is perpendicular to this other line. So just make sure that you understand that concept there with a plane and a line that's perpendicular to it. So they say, using some definitions here, decide whether each statement about the diagram is true. So they give us a diagram that kind of looks like this guy here. We've got a point X, and we've got points A, B, C, D, and so tell us if this is true or not. Points D, X, and B are collinear.
Yes.
You agree with that?
Mm-hmm.
David says yes. Anybody else agree with that? D, X, and B, are those collinear? What does it mean to be collinear?
They're on the same line.
They're on the same line, right? See, Jackson's learning. It's like you don't wait, you just go ahead and spit it out, or you don't get to say it. So they're all on the same line, and we all agree D, X, and B are all on that same line, right? The line, that horizontal line there. So that's true. What about the line AC? And remember, just remembering that making sure that you understand what the difference in these are. What's that top one?
Line.
That's line.
Line AC.
AC. Second one?
Ray AC.
Ray AC. And the last one?
Line
Segment AC.
Line segment. All right.
Is there a special way to
Is
write
it Anna Lee? All right. Anna Lee tried to get this one out very far. I saw her try so hard. She was drowned out by all the other voices. Good try. What's that?
Is there a way to write like the perpendicular, or like one of those things, or no?
Like
say
this?
perpendicular. Well, yeah, but like for line AC, you know.
To say that it's perpendicular? Yeah. So you could say line AC is perpendicular to, what line would I say that was perpendicular to?
DB.
DB or BD, either one would be correct. Right? I can switch them around for a line. I can't switch it around for a ray, because the ray has a defined endpoint, but I can for a line. Right? Like this is, if this is A and this is C, I couldn't write that as CA, because the endpoint is A. But lines and line segments, you can flip the letters around. So that's how you would do that, but it's simple. All right? But AC is perpendicular to DB is the statement that they make, and would we agree with that? Yes, we would, right? Because we have the little line here, the little box there signifying that it's 90 degrees. All right, and she didn't say anything, but man, Brittany was shaking her head vigorously when I said these are perpendicular. Nice job. All right, so angle AXB, last one, angle AXB is adjacent to angle CXD. Somebody that hasn't got their name on the board yet, is that true or false? Is everybody's name on the board? No, we still got some people missing here, guys. It is not adjacent. Anna, right? So Anna says it's not adjacent. Anna, why is it not adjacent? It's not right next to it, right? Adjacent angles have to be right next to one another. In other words, another way to share that is they have to share, one of the rays that makes the angles, they have to share that side, right? Yes?
Is adjacent two adjacent angles both have to be 90 degrees, or could they be any?
Well, they can be anything, actually. So it just means they have to share a common side, right? So like when I did this on one of your quizzes, and I said, tell me if these are vertical, linear, or adjacent angles, and you guys put down linear, this is a linear pair, that's correct. But if that's what you wrote down in your test, I said it's also adjacent, right? So either answer would have been true. If you wrote down adjacent, I said that it's also a linear pair, because I want you to understand that both of those are true. Because they share a common side, then they're considered to be adjacent. So these are not adjacent because they don't share a common side. Even though they share a common vertex, they don't share a common side. Okay? All right. Good question. All right, let's move right along and talk about biconditional statements. So biconditional statements are statements where basically it's only true if this other thing is only if this other thing is true, right? So it's going to have the only in there. So it is Saturday only if I am working at the restaurant. It's a biconditional. Yes.
Sorry, it's just me being inquisitive, but what makes the difference between a adjacent and a linear pair?
So a linear pair, all angles that are linear pairs are adjacent. Okay? But not all angles that are adjacent are linear pairs.
Okay.
So for it to be a linear pair, it has to have one side here has to be a line, right? So these angles 1 and 2 are adjacent here, but if I draw these angles, right, 3 and 4, those are also adjacent because they share a common side, but they're not a linear pair because we don't have a line here that forms the two angles. Does that make sense?
Yes, sir.
Right? And so for a linear pair angles are always what type of angles? When I think about the number of degrees that are formed when you combine the two together. They're 180, and so what do we call that? We say they're supplementary, right? There's complementary, which means they equal 90 degrees, and then there's supplementary. Angle 1 and 2 would be supplementary angles because when you combine them together, you get 180 degrees. Make sense?
Mm-hmm.
All right, so a biconditional statement will include that word only. And so basically, I can't remember if I've written this in here, but sometimes when I do a definition, you'll see me write that. And what that means, IFF means if and only if. And so biconditional statements they use that language. Biconditional statements use if and only if. All right? This will only be true when this other thing is true. So if it is Saturday, it is Saturday only if I am working at the restaurant. And so it says you could rewrite this conditional statement in if-then form by saying if it is Saturday, then I'm working at the restaurant.
So if you're not working at a restaurant on Saturday, then it's not really Saturday.
Well, so let me say this. A biconditional statement is a statement that contains the phrase if and only if. Writing a biconditional statement is equivalent to writing a conditional statement and its converse. So when we learned about the converse where you flip them around, the original statement is only truly a biconditional statement if you can flip it in either direction and both are true. All right? So like in the case of the Saturday one, that may break down because you flip it around, it's like, well, would that be true for this? It is Saturday only if I'm working at the restaurant. If this person only worked at the restaurant on Saturday, then I could flip that around and say, if I'm working at the restaurant, then it is Saturday. If it is Saturday, then I'm working at the restaurant. I can flip those around in either direction and they'd be true. Does that make sense?
Yep.
So that one would be true in the case of this one because that's the only time that that person works at the restaurant. All right? So the biconditional statement below, they give an example here, can be written as a conditional statement and its converse. And here's the biconditional statement. 3 lines are coplanar. 3 lines are coplanar if and only if, IFF, they lie on the same plane. So if that biconditional statement is true, right, this is a biconditional statement, then we can write a converse, we can write an original if-then statement based on this and a converse, and both of those will also be true. So let's try that out. What would be an original if-then statement I can make based on that? Yes?
If 3 lines are coplanar, then they lie on the same plane.
That's right. 3 lines are coplanar. Then they lie on the same plane. All right? Somebody else give me a converse of that. Or we just take the statement and flip it around. We're going to have to borrow some language from the first part here, otherwise it doesn't make any sense. All right? You going to take a stab at it?
If three lines lie on the same plane, then they are coplanar.
That's exactly right. 3 lines lie on the same plane. Then they are coplanar. And so both of those statements are true. So because both of those are true, we verified that our biconditional statement is true, right? One of these would fall apart if our biconditional statement wasn't true. So if I give you a biconditional statement and ask you to prove to me that it's true or false, or tell me if it's true or false, this is how you do it. You'd write the original if-then, and then the converse of that, and look at those individually and see if both are true, or if one of them is false. So they have an example 4 here where they give us a statement and they say, write the converse of it, and then if both are true, then write a biconditional statement for that. So let's do this. If 2 points lie in a plane, then if 2 points lie in a plane, yeah, then the line containing them lies in the plane. Containing them lies in the plane. All right, so that's our original if-then. What would be the converse of that? Jackson, no fraternizing with the people outside, all right? They're not part of this class, okay? They could have come in this class, but they chose not to, all right? So I don't want them to enjoy the benefit of that. All right, what would be the converse of this? For time's sake, I'm just going to tell you, all right? So we're just going to flip it around, right? So if 2 points lie in the plane, then the line, wait a minute, I did this wrong. I did it totally wrong. Why did I do that? If a line lies in a plane, then the 2 points on the line lie in the plane. Alright, did I mess that up enough that you're totally confused, or did you guys finally follow? You get it down? Yeah. Alright. Did Jackson wave at anybody while I was turning around? Did you even catch that? Sure. Would you agree that both of those points are true? Yeah, if you've got 2 points, we know the 2 points form a line. If those 2 points are on a plane, then the line that passes through those 2 points are also on the plane, right? And so no matter how we flip that thing around, it's going to be a true statement. So we can construct a biconditional statement from this, right? And so we could say that 2 points, we could say it either way, right? We could say a line lies in a plane if and only if 2 points on that line also lie in the plane. Right? That would be one way that you might write that. So is everybody clear on that? Biconditional statement? This stuff's kind of like fuzzy, kind of weird, sort of. This isn't like This is why some people that love all the other math classes don't like geometry, because we're used to having like hard, fast rules, and now you're like writing things around, and there's multiple answers, you can say it this way or you can say it this way. It's a little too fuzzy for the strong math brain, right? But is everybody clear on that? All right, you guys know what you got to do this week? I'm going to give you an assignment, right? It matches this, so you'll still have a homework assignment and a quiz on 2.1 and 2.2 next week.
Oh yeah.
But you got to take your test at home, have your parents proctor it. Like I said, there will be an accompanying email to your parents. It should be included all that, so that they know they have to part of the test, and then look for the assignment in Google Classroom. All right? You guys have an excellent